For the last talk in this session, we're going to have Faraz, who's going to talk to us about synthesizing probabilistic programs.
Thank you. Good afternoon. Thank you for being here. Consider the following plot, which shows the value of some variable as it evolves over time. You may not know what this data represents, but the minute you see this plot, your mind starts building models for the data generating process. These mental models of yours reflect structure in the data. For example, you might notice that, on average, the value of the time series is increasing over time. You might also see that there's this peak, which is growing as time goes on, which I'm showing in red, and that there's a collection of smaller peaks in between the larger peaks. Moreover, as a result of having a mental model in your head, you can also do other interesting things, like predict what are the likely values that the variable will take in the future, shown here in blue. Now, interestingly enough, what we're seeing here is the global airline passenger volume between 1948 and 1962. More generally, this question of going from some observed data, which evolves over time, to knowing what patterns exist in the data or what the values of the data will be in the future is a problem humans have faced for thousands of years. The farmers of ancient Babylon needed this kind of analysis to predict and plan for their crop yields. Now, in those days, they used to use superstition and shamans, but today, what we do is statistics. More specifically, the person with the data consults a statistician who uses their domain expertise to build models that then explain to the end user what patterns exist in the data and what predictions. And if you're lucky, the statistician will tell you some estimate of their certainty in their predictions. But this process is very intensive, costly, and it needs lots of training. So in this talk, I'm going to describe a way in which we can automate key parts of the data modeling, interpretation, and prediction pipeline. The key idea is that we're going to go from data to highly sophisticated probabilistic models that very accurately represent the data generating process. Once we have these probabilistic models, which we're going to represent as probabilistic programs, we can use them to find what patterns exist in the data and make predictions for future time points. Here's how it works. We start off with a large space of probabilistic programs that can generate time series data. These programs collectively represent all possible time series data which we could potentially see. We endow this space with a prior probability distribution, which is itself a probabilistic program that tells us how to randomly sample from this space. The third component is having the ability to specify for any program what's the probability that it generates data on the y-axis given the input or time values on the x-axis. Combining these three components, we can use the calculus of Bayesian reasoning to define a posterior distribution over the space of programs, which represent our latest state of beliefs having seen the actual observed data. What this technique delivers is a selection of probabilistic programs that are likely to have generated the data. We design these probabilistic programs in such a way that their surface syntax exposes key structural properties of interest, so we can do syntactic analyses to find what patterns probably exist in the data. In addition, because the probabilistic programs we're synthesizing are probabilistic programs, we can run them in a probabilistic programming engine and use probabilistic inference to get likely predictions. Here's what we do in the paper. In our paper, we provide the first fully Bayesian synthesis of probabilistic programs. And we rigorously formalize the approach using denotational semantics. In addition, what we do is we provide the necessary the sufficient conditions that are needed for this synthesis problem, shown in the last slide, to be very probabilistically well formed. And we define an algorithm that is a synthesis algorithm that's applicable to any probabilistic programming language generated by a probabilistic context tree grammar. We've shown that our synthesis algorithm is sound. For the very first time, we've shown that the sampler for the probabilistic program converges almost surely to the analytic Bayesian posterior. On the implementation side, we've implemented these ideas for two probabilistic programming languages, one a domain-specific language for time series data, and another one for multivariate data tables. And we've benchmarked these results and shown the efficacy on multiple real-world problems. Now, I just want to highlight that in this work, what we're doing is combining ideas from theoretical Bayesian statistics with ideas from programming languages so that we can use statistical theorems related to convergence, leveraging the formalism that comes from PL. The idea that models are represented as programs and defining a semantics for those programs. And we believe that as Bayesian inference becomes more and more used and significant over the next 10 years, that these types of soundness proofs, which combine analyses of Markov chains with a linguistic description of the space over which we're sampling, will become ever more relevant. And especially because this community is very interested in statistical rigor and theoretical rigor. Okay. So, in order for this to work, for the rest of the talk, I'm going to give more of a tutorial that exposes some of the key ideas of the synthesis technique and its outputs. So, to discover patterns and make forecasts from data, we need a time series model. And our probabilistic programs are going to be based on what's known as a Gaussian process, which is a rich family for modeling time series with widely varying patterns. What this GP thing is, it's a random function that takes in a list of values from some space x and returns a list of values in some space y. Now, a standard function has fixed input-output behavior. I give it a list of x's and it returns a list of values of the function at those points, which I'm showing here as a red curve. A random function, on the other hand, has stochastic input-output behavior. Every time I execute the function on the same list of inputs, it gives me a different list of outputs. So the model in your head for what's going on is actually not a single curve, but a whole probability distribution over curves. Now, why are these Gaussian processes useful for modeling time series? Well, statisticians use these to model a wide range of patterns. The key idea that lies at the heart of a Gaussian process is what's known as the covariance, which specifies the shape of the time series and how the values of the function at different points are covary with one another. So in recent work, what some people in machine learning have shown is that I can take these primitive patterns, such as periodicity or smoothness or linearity. I can combine these using sums and products or changes in between the covariances. And what I arrive at are a very large set of time series patterns, such as local variation, periodicity and trends, things with growing amplitude, repeating structure. Once we have a Gaussian process model for a time series, we can discover patterns in the time series by inspecting the structure of the covariance, and we can make predictions for new data by using probabilistic inference. So, very quick intuition for how GPs work. It's that, again, each time we invoke f, it returns a randomly sampled curve. A little more formally is that the joint distribution of the list of outputs is distributed as a multivariate normal, with some mean, here I'm just saying it's 0, and the covariance matrix specified by the function k. And what this k is telling me is that for any pair of points, how the values covary with one another. So every time I execute the program, I can fix 2 points, x and x prime. I can get the values of the function at that execution, and the k is telling me how those two vary with one another. And as we saw on the previous slide, by modifying this covariance function, we can get a wide set of patterns. Now, how do we represent these Gaussian processes? One thing to do is represent them as probabilistic code, just the actual way that we can go from the inputs to the samples on the outputs. But that's a very sort of complicated representation that's implementation specific. It's not useful for seeing what sort of the program is doing. So instead, we represent them using a DSL. What this DSL is telling me is giving me a simple representation of the covariance structure. So in the first row, I'm asking for a GP, which is smooth, with mean 3.4, and those are the executions you're seeing in the first plot, just some set of smooth curves around 0. In the second row, I'm showing GPs, which are representing a periodic and linear structure, taking the product of those two, and you're seeing multiple executions of that random function. In the third row, I'm asking for a Gaussian process, which is changing at some point in time between some linear trend with white noise before 4.5 and some periodic trend after 4.5. Now, it's quite straightforward to write a context-free grammar for this DSL. I have some set of numeric parameters that parameterize the covariance. For example, the linear slope, or the how smooth it is, or the periodicity. And I also have some composite rules, which are taking sums and products or changing in between these different covariances. Okay, so one question you might ask is, you might look at this sort of roadmap and say, you have this thing called the likelihood. Why don't you just find the single program that maximizes the likelihood of the data, or the probability of the data? It's a perfectly reasonable question, and hopefully I can give you a visual intuition for why that's not ideal in our case. Suppose my observed data has the following form. What I can do is I can synthesize or devise a DSL program P that models this data arbitrarily well. Roughly what it's going to do is our space is so rich that we can simply define a program that linearly interpolates between the points, just changing between these lines with a little bit of noise. Now, as I take this noise smaller and smaller, I can get the data likelihood arbitrarily high, even though the program that I've synthesized is useless, because it doesn't represent any actual structure in the data, and it doesn't tell me how to forecast future data. On the other hand, a much simpler program is one that says there's some periodicity and some noise, and this program, in fact, with the periodic structure, has a lower data likelihood, but it's simpler and it's much more useful than the highly complicated program that's simply interpolating between the observed data. So by having a prior distribution, we can prevent overfitting. And what this lets us do is not focus on probabilistic programs or DSL programs that are too complex without there being sufficient evidence. Now, this argument can be made rigorous, but the intuition here hopefully is clear. The second question is, well, okay, we have the prior and the likelihood. Why don't you simply find the program which is the most likely under the posterior distribution? It's another fair question. And hopefully here I can also give you an intuition for why that's not necessarily the best choice. So suppose my observed data has the following form, and I hypothesize two candidate DSL programs for the data. One is some linear trend with noise. Another one is some periodic and linear trend plus some noise. Now consider this scenario, where my unobserved data is shown in red. In this case, the predictions from my linear model are pretty good. Even though it may seem to somewhat underfit the observations, it actually gives reasonable predictions, whereby it's clear that my periodic model has completely overfit because the periodic structure does not correctly generalize. Now, in scenario B, where there is in fact periodic structure, my linear model gives me an underfit. There's data points which are clearly outliers, whereby my periodic model actually gives me good predictions. The higher level point here is that by synthesizing multiple programs, what we can do is we can compare and combine multiple hypotheses for the data in a rigorous way. There's not necessarily even a most likely program. These posteriors may be multimodal, and by sampling, what we can do is combine these and many other programs to get an idea of what the data generating process might be, averaged over multiple different possible scenarios. Okay. So now let's look a little bit about the synthesis system. Now, I just want to highlight here that what we're doing sort of is a key departure from the majority of probabilistic programming work, because we are not trying to estimate the parameters of a fixed probabilistic program. We are trying to synthesize the text of an entire probabilistic program from scratch, and in addition, the parameters of those programs. That's a much sort of more a much higher level operation than having a fixed program and estimating the parameters. Moreover, we implement the synthesis technique itself in a probabilistic programming system, which is known as Venture. Here's a very quick tutorial as to how that works. So I have my observed data, and I can load it in. I sample an ensemble of these DSL programs from my prior distribution, which I've described. And then I can run my synthesis chain. And what that does is it goes from the initial set to a set of posterior samples. And I can use that then to obtain forecasts on held out data or on future data. Now, good question to ask, especially if you're working on some machine learning applications, are the outputs of your technique accurate? And what we've done is actually shown that, at least against a wide set of baselines, which also are mostly automated, this technique is able to capture more structure as opposed to other statistical methods that are widely used in the machine learning and statistics community. And these generalize to a wide set of other real-world data sets from economics and from healthcare and from temperature and so forth. The second question that I sort of emphasized at the beginning of the talk is not only are we interested in forecasting, but also in detecting structure in the data. So what I'm showing here are just a collection of programs synthesized in Venture. Because these programs are represented as first-class objects in my language, I can write syntactic analyses which walk over these data structures and start doing things like computing the probabilities of various structure existing in the data. So here I'm showing 5 real-world data sets and 1 simulated data set, and I'm showing that what you can do is get a posterior estimates of my uncertainty that there are change points in linearity and trends in the data. Now, briefly, if we look at this a little bit more clearly, as okay, you talked about the prior, but you didn't describe it. Well, it's actually quite simple. Is we take our context-free grammar and we make it probabilistic. So we add these production rule probabilities and these probabilities for terminal symbols. And the code itself in Venture is not that important, but roughly each component of the PCFG corresponds to some code in Venture. So here the production rules are just sampling statements, as are the terminal symbols. Statements in Venture. And the flexibility of Venture is really what's essential to be able to write priors over program text and do inference in those programs. Now, we also write a small interpreter for the DSL program, which takes the DSL and returns what's known as a Venture stochastic procedure. And this allows me to leverage probabilistic inference in Venture and simplify my synthesis by reusing the machinery, the general purpose inference machinery in the system. And finally, there's the Bayesian synthesis algorithm, which is a big component of the work. And what we've shown in the main paper is that the synthesis algorithm is sound for any PCFG, not just the Gaussian process DSL. And I'll refer you to the paper for more of those details. So finally, what I'll spend a few minutes talking about is this notion of formalizing structure discovery, which is something in machine learning and statistics from the lens of probabilistic programming. One reason we might want to do this is reducing implementation complexity. So here what I'm showing are lines of code counts, or approximate lines of code counts for various implementations of time series structure discovery. And you can see, even if you take these numbers as a ballpark estimate, that there are significant gains by reusing inference machinery from probabilistic programming as opposed to manually implementing samplers. Now, the second point, which I talked about earlier on in the contributions, is giving a PL description of what are typically statistical or informal descriptions and using the notions of domain-specific languages to encode model structures and using numerical constants in a program to represent parameters, and representing Bayesian inference as a synthesis problem shown in the right-hand column. Now, you might think that it's enough to just write sort of any prior over programs for this to work, but in fact, if we know anything about reasoning about programs, it's that it's very subtle. It can be challenging. So in work from 2011, Ackerman, Freer, and Roy showed that posterior distributions may not be computable or they may not exist at all. And these are the conceptual issues really at the heart of the work that we're looking at, right? There are other theoretical issues, such as, is the prior well-defined? Is the likelihood of the data finite? Does the posterior exist? Does the inference algorithm converge? And these are all very important questions which we try and tackle in the paper. So I'll skip over most of the semantics because those are not super important, and some of the ways which, at least for a PCFG, you can solve the halting problem due to some classic work in '73 by Booth and Thompson. And these semantics are all in the paper, not super important. And just from the lens of where this work lies in the broader ecosystem of synthesis techniques, what we've described here is a fully Bayesian synthesis technique for probabilistic programs. And there are people who've worked on non-Bayesian synthesis of probabilistic programs, probabilistic synthesis of non-probabilistic programs, and then the much wider work of non-probabilistic synthesis of non-probabilistic programs. And so this is sort of where this contribution lies, and where we think this community can help us is by using formal Bayesian methods for program synthesis. That's all. I'll be happy to take any questions.
All right, thanks a lot for the talk. I'll take questions from Slido. If you have any questions, please flag me down. The first question was about kind of usability, I guess. So could you comment on how much expertise a user needs to kind of devise a DSL for their task, or how to use this kind of system?
Exactly, that's an excellent question. So here what we find is that devising the DSL is a language design problem. This is something which people who have expertise in statistics or programming languages devise DSL, and we can leverage a lot of the insights from machine learning for doing that. And in the paper, we show how to do it for time series and for tabular data. Now, from the perspective of the user, we don't expect users to be defining DSLs, but rather using the outputs of the synthesis system and delivering programs to them to use. Yeah.
So in Gaussian process, I heard if you choose the wrong corner, then the sample path is not necessarily continuous. And then do you encounter any of these issues?
Can you please repeat the question?
So in the Gaussian process?
Gaussian process.
Yes. If you choose the wrong corners.
The wrong?
Yeah, so
kernels.
Yes.
Right, covariance
then
kernels.
You might end up with showing that sample path almost surely continuous requires some extra work. So do you do any of these kind of things?
I'm not sure I fully understand the question.
So right now, you explain Gaussian process. And
Correct.
Typically, people explain Gaussian process as a distribution of functions.
Yes.
But those functions is not necessarily continuous.
Correct.
So then I'm just worried that that might cause any issues in your modeling language, because your modeling language generate kernels automatically using your domain-specific language.
Correct.
So does that have any such guarantee, or maybe it doesn't cause any issues with you?
Yes, actually, I see. So one detail here is that one thing that we put onto the DSL always, and this is actually essential for the correctness of the likelihood to be bounded, is that there's always some white noise on the output of the covariance kernel. So we synthesize a covariance kernel and add a little bit of Gaussian noise. And then if the data may not be continuous, the Bayesian posterior may not converge to the data generator. But our synthesis algorithm, what we're showing is that it converges to the posterior on the data. So there's one question, which is, does the GP converge almost surely to the true generator? And that's not really what this work is trying to show, but instead that the synthesis algorithm converges to the posterior. The behavior of that posterior, I think, is a very interesting question. But it is essential for us to add a little bit of noise on the output so that there's all this there's continuity in the programs that we synthesize. I'll be happy to elaborate more, discuss afterwards.
All right. I just had one more quick question, summarizing some of the Slido questions about the prior. So some people wondered, how is a prior chosen, and does it have a large effect on kind of the result of the synthesis, or the performance, or the accuracy, or however you like to measure?
Thank you. So the prior has to be chosen. This is sort of a part where I went pretty quickly. It has to be chosen in such a way to ensure that the expectation of any program's length is finite. Now, this is maybe a little bit subtle, but you have to ensure that the production rule probabilities don't cause the branching factor to be too high, because otherwise your prior may not be normalized. And that's roughly what I was trying to show in this example, where I can have one program where the prior is not normalized simply because I'm creating more computation than it will need to terminate, and another one where it is normalized, and there's a static analysis of the PCFG itself that we can determine whether that's the case. The question of prior sensitivity, I think it's a very good one. Here we've specified, broad priors, but if there's domain knowledge, for example, if you know that the data changes a lot, you may wish to tweak some of the prior probabilities of these different kernels, and that's where you can encode your knowledge in the data.
Great. Let's thank the speaker again.
Thank you.